Review sections 8.3 through 8.5 on systems of equations. Section 8.3 is focused on solving system of equations by using the addition method. Solve by addition. So we're given two different equations. We would set them up just like we do a basic addition problem vertically. Align your x's, align your y's, keep your signs, and align your solutions. So when we add 2 plus 4, they're both positive, we would get 6. Y plus y is equal to 2y. And our x's end up canceling each other out because we have a positive and a negative. So then we would solve for y. Divide both sides by 2, and our answer is y equals 3. We can substitute y equals 3 into the equation and solve for x to get x equals 1. The addition method. Multiply each term of one or more equations by some non-zero integer so the coefficients of one of the variables are opposites, like the x, positive 1 and negative 1. And then you can set them up just like we did, adding so that one variable is eliminated, and that gives us the answer that we can replace into the other equation. And then we can check both solutions to make sure that they work. So here's an example where originally we're not given numbers that would end up canceling, but I notice that if I took my second equation and multiplied it by negative 3, that would make this become a positive 3y, and therefore the negative 3 and the positive 3y would cancel. Just like they do here, we would solve for x. We're left with negative x equals negative 4, and then we can just multiply both sides by negative 1 to get a positive value. Our other example here, if we then just kind of finish and check and make sure that that works, we can substitute x as 4 in for our solution and get a y equals 2. Solving by addition again, even if we have fractions, we can multiply those fractions so that we end up with a value that is a whole number that would give us the opposite for our variables so that we could subtract those values. So in this case, we're going to multiply each term of the equation, the first equation, the fractions, by 8. And that would end up with 12x minus y equals negative 8. Well, this equation is still not set yet because I want to get that y as a negative 3y. So I'm going to multiply again each term by 3. And if I do that, then I do end up with two equations that are ready to be added because we have a negative 3 and a positive 3, which would cancel out. Those 3's cancel out. We're left with 52x equals negative 52. Divide by 52. We solve for x, replace that into our second equation, and we get a solution of negative 4. We could check that to make sure that that works. Even if we're working with decimals, we can still multiply as long as we're multiplying by the same value in each area here to make them whole numbers. So to make all of these a whole number, the nice thing is they're all written as hundredths. So to make it a whole number, we would have to multiply every number by 100. So we're just moving that decimal place over 2 to the right. Now we have whole numbers that we can work with. It should be a lot easier. Then we can determine what can we multiply each equation by to end up with a value where we have opposites that would cancel out. And in this case, we can multiply the first equation by 3 and the second one by 5 so that that second variable becomes 15 because that would be the least common multiple between 5 and 3. 5, 10, 15, and 3 times 5 is 15. Once we solve for x, we can replace that in to solve for y, and then we can check to make sure that it works by replacing both equations, x's with a negative 1 and the y's with a positive 2, and it does end up working. Section 8.4, we're going to review the methods for solving the systems of equations that we learned in 8.1 through 3. So we can use substitution. It works well if one or more variables has a coefficient of 1 or negative 1. Addition works well if the equations have fractions, decimal, coefficients, or if no variable has a coefficient of 1 or -1. And here's some examples. Let's take a look and figure out which method would be the best one to use. In the first example, the addition method should be used since none of the variables have a coefficient of 1 or -1. The second example, we could use substitution since x has a coefficient of 1. And in the third one, the addition method should be used since none of the variables have a coefficient of 1 or -1. So let's solve the system algebraically. In this case, we can multiply each term by 10 to make all of our numbers whole numbers. Then let's choose to multiply by 4. The first equation right here, this 5x minus 3y by 4. And the second equation, we're going to multiply by 3. And why are we doing that? Because we wanted to find a least common multiple between 4 and 3, which is 12. So if we're multiplying this by 4, everything needs multiplied by 4 to keep it even. And same with the bottom. If we have to multiply 4 by 3, then we're going to multiply everything by 3 to keep it even. Now we have a 12 that's positive and a 12 that's negative to cancel. And then we can solve for x and substitute to solve for y. We can then check our solutions to make sure that they work in both of our equations. Here's another one. Let's look at what we're given. Okay, we want to solve equation 2 for x since there is, I look and see, oh, look, there's no number in front of x. There's no coefficient. So that makes it easy to solve for x, and this is called the substitution method. So I'm solving for x. I'm replacing what I get, the 7 minus -2y plus 7 in for y in my second equation, and then I'm solving to simplify my numbers here, and what do we end up with? We end up with 21 equals 12, and that is not a statement that is true. So if you do not get a correct answer, or there's no statement that is true, this means there's no solution. So if graphed, these lines would not intersect at a point. They would have to be parallel because it's either they have many solutions where they're on the same line, they have one solution where they intersect one time, or they have no solutions, they are parallel to one another. And here's another example. Solving these algebraically, we can look and see, well, it's kind of hard to solve for a one variable, so let's find a least common multiple, which would be 24. We have a positive and a negative. So we'll multiply all of the first numbers by 6, all of the second equation numbers by 4. That gives us a positive and negative 24, which cancels out. It also ends up giving us a positive and negative everything. So we end up with 0 equals 0, which means this is the same line. These graph lines are the same, so there's an infinite number of solutions to this system. So remember, here's our 3 options, and if there's one point, we would just end up with, x equals this and y equals that. If we have parallel lines, there's no solution, and if the lines intersect, everything's the same. In our last section, 8.5, we're going to look at word problems that solve systems of equations. Here's our first one. We have Strongsville High School is holding their annual musical. 650 tickets were sold for a value of $4,375. If adult tickets cost $750 and student tickets are $350, how many of each kind of ticket were sold? So first we need to figure out let's make sense of the problem. Let's write an equation to make sense of the problem. If we have adult tickets and we add them to student tickets, that means we sold 650 tickets. Okay, x plus y equals 650. Write the second equation. The value times the number of adult tickets, 7.5, so that's how much an adult ticket costs, times however many tickets we sold, plus it was $350 for each child ticket or student ticket, equals $4,375 total value of money. So now we have 2 systems, 2 equations. We can solve and state our answer. In this case, it's easy to substitute because we have no numbers in front of our first variable. So solve for x x equals negative y plus 650. Replace that in for our second equation of x. Solve for y, we get 125. Substitute that back in, x plus 125 is 650, so x equals 525. So our solutions are 525, 125. So what does that mean? It means there were 525 adult tickets sold, 125 student tickets sold. We'll plug those into our equation and make sure they work, and they do. All right, we'll do one more example. A candy company wants to produce 20 pounds of chocolate with 45% fat content. To obtain this, a 50% content chocolate is combined with a 30% fat content chocolate. How many pounds of the 50% fat content chocolate and how many pounds of the 30% fat content chocolate should be used to make the desired 20 pounds? So we know that x, our 50% fat content, plus our y, 30%, is equal to that 20 pounds that is desired. And as a decimal, 50% is 0.5 times x, pounds of candy, and 0.3 times y, pounds of candy, is equal to 0.45 times 20 pounds of candy. So now we have two systems of equations. We actually can multiply that out. We end up getting a whole number, which is 9. In this case, again, we don't have a number in front of our variable, so we can solve for x, replace that in, solve for y, and replace that in, and we get 15, 5. So what does that mean? The candy company should use 15 pounds of 50% fat with 5 pounds of 30% fat to get the actual amount that they were looking for, and we can check our solutions to make sure that they are verified, and they are. And that concludes sections 8.3 to 8.5.